Hello again. This is a short introductory video on the electric field and electric potential due to point charges and the way you'll use them in this lab exercise. So every charged particle has electric field emanating from it. Right, here's a positively charged particle. The field lines are pointing away from it, which means if another positive charge was near this thing, it would be repelled by it. A negatively charged particle would be attracted toward it. And of course, negatively charged particles, the field lines go toward them, which means if a positively charged particle was near this, it would be attracted to the negatively charged particle. And a negatively charged particle would be repelled by it. So here's the field due to two particles that are near each other. The field lines emanate from the positive charge and go into the negative charge. Now, for a third positively charged particle that's in this field, the force on that particle would be in the direction of the arrows of the field. So, say this point right here, the force would be in this direction. And the strength of the force is proportional to the density of the field lines that you see here. So out here the field lines are not so dense, and so the force is relatively weak, but in between the two particles the field lines are densest there, and so the force would be at a maximum right there. So this shows the direction of the force on a positively charged particle. A negatively charged particle would be forced in the opposite direction. Now here's another configuration of charges. This is, say, two electrically charged wires that are near each other. One has a positive charge, the other has a negative charge. Or you could think of it as a side view of two capacitor plates. You'll be studying capacitors later on in the semester. When you charge two plates of a parallel plate capacitor, that is, when you put a voltage across them, one of the plates takes on a positive charge, the other a negative charge, and so there's an electric field between them and around them. Again, you can see that the field between the plates is quite strong, the high density of electric field lines, and outside you have some field, but it's not as strong. So a positively charged particle would be forced toward the blue plate, a negatively charged particle would be forced toward the red plate. Here's a practical application of electrical field. This is the electric field around some sort of protein molecule. And molecules, of course, are made of atoms, and atoms are made of protons, neutrons, and electrons. The protons and electrons in a molecule are typically not distributed in exactly the same way. So there's some places with excess negative charge, and that's where you see it's blue, and there are other places where there's excess positive charge where it's red, and so there's electric field between them. And these electric fields, due to especially these big biological molecules, are very important because the molecules interact with each other in that way. For instance, in a cell membrane, the molecules are held together by these electric fields. I mean, electric fields are also responsible for holding electrons to atoms and molecules together in covalent bonds, but these external electric fields are very important in the dynamics of molecules, and especially in biological systems. Okay, what you're going to be doing mostly in this lab is calculating some electric field strengths and electric potentials at various points due to charged particles. So I've got the equations for electric field and electric potential here. Now, although the equations are quite similar, these are very different quantities. The electric field, they have different units. The electric field has units of force per charge, newtons per coulomb. So it's the amount of force on a given amount of charge. Potential has units of energy per charge, so it's the potential energy. I'll explain that in just a bit. And K is Coulomb's constant. It's this very large number, 8.988 times 10 to the 9 Newton meters squared per Coulomb squared. And you're going to be using these equations to calculate some field strengths. So for instance, in this kind of a configuration, the field between the two particles would be the sum of the fields due to the individual particles, and the potential between the two particles is the sum of the potentials due to the two particles. And you're going to be doing some of this in the lab. So for example, let's say we have this positively charged particle here, and we want to find out what is the electric field at this point over here, and what is the electric potential at this point due to this one charge. So let's say, for instance, it's a 3 nanocoulomb charge. Nano means a billionth. That's it's lowercase n is the metric prefix for 1 billionth. So that's 3 times 10 to the minus 9 coulombs of charge. And the point we're wondering about is 2 meters away. What is the field and the potential at that point due to this 3 nanocoulomb charge? So first let's do potential. Here's the potential equation. We put in the numbers. I put in the coulombs constant, 3 times 10 to the minus 9 coulombs, 2 meters for the distance, and that turns out to be 13.5 joules per coulomb. So what does that mean? That means that if I brought a coulomb of charge into that point from far away, it would require an input of 13.5 joules of energy to do that. And 2 coulombs would require twice that. So it's the electric potential at that point, the amount of energy per charge that you'd have to put into to get it there. So it's the potential energy that charge would have at that point. What about the electric field? Well, here's the equation for electric field. Put in the numbers, and you get 6.74 newtons per coulomb. So this is units of force per charge, right? If I had that coulomb of charge at that point, the force due to the 3 nanocoulombs of charge would be 6.74 newtons, and 2 coulombs of force would be twice that. Okay, so this is force per charge. So let's put those numbers by that charge to show that for that point, these are the potential and the electric field at that point. Now let's put in another charge. Let's say a negatively charged particle, and let's say we got minus 2 nanocoulombs, minus 2 times 10 to the minus 9 coulombs of charge, and it's 1.5 meters away. So I put in the numbers for the potential. I get minus 12 joules per coulomb, and the field is minus 8 newtons per coulomb. So what do the minus signs mean? Well, if I brought a coulomb of positive charge into that point, the potential due to the negatively charged particle would be minus 12 joules. In other words, 12 joules of energy would be delivered to my hand or whatever it is bringing the charge in there. And minus 8 newtons per coulomb means that minus 2 nanocoulombs would be attracting the coulomb of charge at that point with a force of minus 8 newtons, meaning it's attracting it. That's what the negative sign means for that. Okay, so here's the numbers for that charge. Now what about the total potential and the total field due to these 2 charges for that point? Well, the potential is fairly easy. It's just the sum of the 2, right? You just add them up and you get 1.5 joules per coulomb at that point. So if I brought a coulomb of charge into that point, it would require 1.5 joules of energy. That's the potential energy of the coulomb of charge at that point. Now what about the electric field? Now electric field, of course, is a vector quantity. It has a magnitude and a direction. And by the way, the direction of the field toward the negatively charged particle, it should be pointing directly at it, but my drawing is bad here. Anyway, you get the idea. These are in 2 different directions, and the sum of the electric field due to those 2 is the vector sum. So it would be in this direction. So the magnitude of the electric field at that point is not just you can't just add the numbers together. You can't add minus 8 newtons per coulomb to 6.74 newtons per coulomb to get the field strength. You have to add them by components. And if you remember adding vectors by components from the first semester, 1111, you'll remember how to do this. If you have trouble with that, I'm glad to help you refresh your memory of how to add these by components. This turns out to be, the magnitude is 10.5 newtons per coulomb, and you can actually find the direction, again, with a little trigonometry. Okay, so this is the basis of how you find potential and electric field due to charged particles at different points. And again, I'm ready to help you with these problems when you're doing the lab.